Welcome everybody, and thanks for joining. This is our showcase presentation, which is meant to sum up the work that we have been doing in the area of interactive C++. And today we're going to look into the motivation why we started doing this. We're going to quickly go over the exploratory programming with C++ and the compiler as a service as a concept. Then we're going to dive a little bit deeper into the project goals and implementation. We are going to look into how we support incremental compilation, how that helps us to do language interoperability, how we can steer some heterogeneous hardware support, what we have done in the area of tutorials and community outreach, and we're going to have a live demo. Hopefully things are working fine, as I know that it's a notorious source of failure, but I think we're brave enough to do that. And we will summarize what's in terms of future work. So for motivation, C++ is one of the programming languages that's used for numerically intensive scientific applications, especially the ones that need to go to exascale. There is practically no other choice. But however, C++ is often seen as difficult to learn and inconsistent with the rapid application development. That is where you want to just type something real quick, see how it goes, and then iterate. And of course, the use of new programming languages has grown steadily in science. And in fact, since quite some time now, Python is the language of choice for data science and application control. But its computational performance is kind of mediocre. And our motivation was that we wanted to look into ways how we can combine the expressiveness into Python and the powers of C++, but not creating a new language where people need to learn and then it has all its own pitfalls. Just to step into a little bit the interactive C++ and exploratory programming, my animation is off a little bit. The key insights on interactive C++ and generally interactivity is to be able to close the loop between edit and run cycles. And for us, incremental compilation is a key where you have like a translation unit which grows within each input, gracefully handling errors like syntactic and semantic errors, being able to like undo something that either you mistyped or you just typed wrongly in terms of semantics. We want to be able to execute statements. As you can see here in my example, I can just replay that. In my examples here, you can see diagnostics, but you can also see that you can real quick type statements on the global scope, and we want to be able to display execution results, like easily to see what's behind data structure, because we want to do data science in the end. And we want to be able to help users with their way of using the system by allowing certain entities to be redefined. And these are properties that are like very common for duck type languages like Python, but there's no inherent reason for not being able to do that in other statically compiled languages. And as a matter of fact, whether a language is interpreted or compiled is an implementation choice. And based on that implementation choice, of course, if you have only implementations that compile your language evolution is going to go into making certain choices to back up these major use cases. But there's no inherent reason for why you can have like an interpreter and a compiler for the same language. And C++ is one of these examples because we have built interpreters, and they go quite a long way here. Now, if you want to kind of generalize that concept, is what we call compiler or C++ as a service. This is basically our vision is that when you have an application, you have multiple stages. One stage is where we develop the application, then we deploy it, then we start it, and then we execute it. And those different steps generally happen at different stages of the lifetime of the software. And normally when we develop the program, we program for some abstract machine or abstract user. And we want to be able to like cover all possible use cases and users. And of course, in the end, the software goes to a particular target machine and a concrete user with concrete use cases. And here, the static compiler covers pretty well the development cycle only, because it needs to imagine what would be the machine afterwards. However, generally, it's able to kind of do a lot of performance optimizations at compile time, because it forces you to express your program while thinking in terms of like what can be folded away during compilation time. But it misses quite a lot of opportunities in terms of like whenever we deploy the binary, we know pretty much where what the target machine is going to be. And whenever we start the binary, we know what kind of use cases are we going to have. And when we execute, we collect data from the user experience. And those are like opportunities which we can use for further optimizations. And these parts of the flow are generally known as ahead of time when we deploy and before we start, just in time when just at the point where we start the binary. And then the binary execution. This is the continuous optimization that we can. We're not going to go into too many details here, but in general, we can continuously optimize our software. And if you think of it, the static compiler in some languages, and now with our project in C++, can defer certain operations for the runtime compiler. And by saying runtime and compile time, people tend to think that runtime is slow, compile time is fast. But if we are smart enough, we can ask the static compiler to defer certain operations just to make use of just to improve performance. And one example here is for C++, we have a notorious combinatorial explosion problem where we have templates, heavily templated libraries, which need to provide template instantiations for gazillion types of the user, because we don't know how the user is going to use stuff. And one of the examples here is that the compiler as a service can come to an aid and actually help us with actually instantiating the required type, and not the library author to guess what types people are going to use it with. And vice versa, the compiler as a service also can export some information to the previous steps and actually help optimizing further. And one classical example here is this profile guided optimization, which runs a set of tests or a set of use cases and then collects information where your branching is and so on. And it's able to instruct next static compilation to make better branch predictions and so on. So the whole point of I think this talk and the project is how we can smartly merge those two different concepts into one, which can come to the benefit of the scientific use cases that we have. And just a step further into what I'm talking about is that our programming model, after these 3 years of development, essentially allows us to kind of incorporate classes, like embed the compiler as a service. And in that case, we have the Clang C++ interpreter inside our code, which is compiled by our favorite compiler. And it can call like an interpreted function, which in practice, it can be anything that goes and says, interpreter declare, does some code. And then the interesting thing is that you can bridge the compile time and runtime. And you can see here in that case, we define some function cube, and we, of course, here, if it's like a hotspot, we can instruct the compiler as a service to spend more time in optimizing it. And then what we can do is we can get the address of that interpreted function at compile time, and then use it as a normal function pointer call. And you can just, invoke it and run it. So this is the sort of merging of those concepts, and this is the experience that we had over the years with the interpreter Clink and the field of energy physics. And this project is essentially going in the direction of trying to mainstream that to broader scientific communities. And our goals are our project goals, and we're going to look into how we have or have not achieved them. I do think we have achieved most of what we have proposed. Is to leverage the infrastructure that we have already developed in the field of energy physics and make it available to the other scientific domains via LLVM and open source. So what we want to do is we want to generalize all these concepts, make them acceptable for LLVM from the compiler engineering standpoint, and deploy them to other scientific domains. So the support for incremental compilation here is critical. So in our early stages of the project, you can see here in the screenshot, move this, is that on July 2020, in July 2020, we have started a discussion whether or not it's a good idea to move parts of what we have built in closer to Clang and closer to the LLVM orbit. And this was like a critical part of the project because depending on how this community would react to that idea, our lives could have been much harder. So in the end, it was a very positive outcome because people have learned about what we have been doing and they were excited about it, and they knew that we could implement it in a non-intrusive way into the LLVM infrastructure. Or if they didn't know it, we convinced them that we could do it in that way. And then shortly after, we have had our first commit on the compiler as a service project. So we have our clang-repl, which is the generalization of the compiler as a service and the Clink project into LLVM mainline. And our initial infrastructure landed in LLVM 13, and there have been gradual improvements ever since, and we're currently at LLVM 17. Since LLVM 13, while I was preparing these slides, I realized that next to our team, there were like a bunch of developers that were continuously improving what we have built and refactored it and made it better and made it more consistent to the rest. So we have approximately over the years 30 developers that have contributed in that area, different than the usual suspects, which I think is a good sign that the maintenance costs are going to be in the end reduced. Here, one of the big challenges for the field of energy physics was that once we have built this started as a proof of concept, and we have been reluctant to upstream some of the work to the LLVM mainline, mostly because we were not sure whether we were going to get where we wanted to be. And then the next thing was that we were fixing critical bugs for deployment and so on, and then we didn't have the time to write proper tests and go through the proper LLVM reviews. And over the years, that has been quite problematic because we accumulated a good amount of technical debt, and it was challenging to iterate and to improve the current system. So part of the project was that clang-repl actually provided environments inside LLVM, which combines a couple of components and gives a good test bed for what we want to show people. For example, we will have a way to test our workflows and then make sure that nobody else afterwards break them. And until then, that has been a problem. And it has been a problem for tools like LLDB and so on, because they also didn't have that component. And now this is also fixing these kind of workflows. So once that was done, we were in a position to start uploading our patches in a testable and more structured way. And here, most of the patches that are related to the, incremental compilation have been uploaded to LLVM 17, and the LLVM 17 was released yesterday, I think, or like within like the last 10 days. And here I'm gonna try to call out a few people that have helped over the different projects, but this is not an exhaustive list. And I apologize in advance if I have missed somebody that has done something really significant and I did not capture that here, because to my defense, I can say that I had to prepare that slide for like 2 days or so. So anyway, so here one of the key players was like an unfunded contributor, Tapasveni Patak, who uploaded a bunch of slides. A Google Summer of Code student, Jun Zhang, and Jonas Hanfeld, who managed to put all of this together. We have upstreamed, as I said, the essential patches, and here as an outcome that helped us upgrade help us speed up the LLVM upgrade cycles in the field of energy physics, so our major scientific domain. And to give an example, so very roughly the time from upgrades went down from approximately 1 year. It took us 1 year to upgrade from LLVM 5 to LLVM 9, to several months from LLVM 9 to LLVM 13, and to several weeks from LLVM 13 to LLVM 16. And here, of course, there is a lot of subjective factors. It depends on what kind of changes were done in LLVM and so on. But the trend, I think, at least for me, here is obvious. The other improvements that were related to clang-repl were it actually helped drive several developments. For example, we had automatic completion, like automatic tab completion, improving the overall user experience. Like that will be a new development, and it's going to be released in the next LLVM release, LLVM 18, by Yuchan Fu. So here it was very interesting that we managed to kind of piggyback to the rest of the infrastructure, and we are using essentially the same code where Xcode uses for auto completion. So that's pretty exciting here. The other thing is that we managed to implement a shared memory manager for JIT Link that enables efficient out-of-process execution to improve the system stability. That's available in LLVM 15. So that's basically allows you to run user code in a separate process if you have like a out-of-process execution. So the shared memory allows you to kind of reduce the RPC calls so that you could still get to some comparable performance results. And the major other development was that it helped implementing quite a bunch of JIT Link backends. So the JIT Link is that technology which helps move the static linker and the thing that helps the JIT to link object files into memory. And that's like a new thing because overall, over the years, there have been a lot of developments which were different from the nature of the static linker. And this is kind of, this technology is merging both of them, which means that when you are executing C++ code at runtime, it's very, 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 very close to what you would be doing when you have it statically compiled. And our group helped develop the ARC64 support that's available in LLVM 15. The PowerPC support was contributed by somebody else. I will come back to this. So the Windows support also. And we'll come to some more details here a little bit after. So the next major item is that once we have put the basic infrastructure in place, we wanted to make it available in platforms which are de facto standard for data science. And one such platform is Jupyter. The way that you run code in Jupyter outside of like Python is through this specific kernel protocol, which you can write if you derive from some class following this protocol, then you can plug in your execution system into Jupyter, into the Jupyter infrastructure, and then use it there. So the release schedule of clang-repl And the packaging with LLVM enabled quicker adoption, quicker turnover with what happens within the Jupyter system. So one of the projects that we have started, and here that's going to be hosting our major developments, and we're going to use it to demonstrate what we have in terms of demos, is the so-called Zeus clang-repl project, which enables incremental C++ with interoperability extensions, so we can run Cuda and Python at the same time through this system. The other thing, which was developed in a collaboration with the Quantstack company, was Zeus CPP, which enables clang-repl in Jupyter Lite. And the major difference between Jupyter Lite and Jupyter Lite and Jupyter is that Jupyter Lite has a mode which can run into WebAssembly mode, so it would execute code inside your browser. So you don't need to have like a computational resources in the cloud to be able to run simple things, and this is very useful for education purposes. And we have also developed a WebAssembly-based clang-repl in Jupyter Lite. We're going to have a very quick preview of what we have here. And of course, here it's an effort from multiple people, multiple projects. People to call out here is Alexander and Nubhat and Silva and Ioana, who have been putting a lot of work in these things over the years. Moving on to the next step, once we have put C++ inside the Jupyter notebook, and we want to be able to connect it to other ecosystems. Because the C++ ecosystem is quite vast, but it's also very useful if we can combine with languages like Python to be able to use C++ for what it is good for, and then use Python for what it is good for. And actually, this was our mock-up in our very early stages of the project proposal. So you can see here we have like a single Jupyter notebook, which defines some C++ entity. Then we have like a bunch of an interoperability layer, which takes this, as you can see here, that information of struct S and instantiates from within Python an STD vector of S. And then in the next cell, that's number 4, we can also create a class that in Python, a Python class that derives from S, which S is like the C++ entity, and does something else on top. And then to make things even more interesting is we also want to be able to run Cuda kernel and then record its results back to that environment. So what we propose here is essentially having some sort of a uniform language environment where the language becomes just a front end, and then on the back it's just one thing, one set of memory that we access through different language rules and reasons. And we're going to go back to that during the demo. So one of the challenges here, how other people do it, is you can do it in multiple ways. One way is to do some sort of marshalling, where one language would serialize its state or the relevant state and then transfer it, and then the other side would be unpacking it and so on, and that's quite expensive. So crossing that language barrier generally is expensive in the implementations, but our compiler as a service provides a different approach to this and makes it extremely cheap. We're not going to get into too much details on this, but this language barrier, we're able to kind of speed it up and then really provide an uniform system which you can optimize both representations from C++ and Python to make things even faster. I'm not going to spend too much details on that, but this is quite exciting, and maybe it's a subject for other presentations. So the way that we chose it is, if you are familiar with the field of energy physics, you probably know that there is a tool that people refer to PyRoot or CPPIY. So this is like a quite interesting approach to language interoperability between Python and C++. So it's more performant than the usual bindings, and it's more flexible because it has, in the end, compiler as a service in the backend. So whenever Python asks for something in C++, then the C++ compiler knows very well what needs to return. And here the major advantage is that this can be applied to any C++ library that you have out there, or any C library that you have out there, because it doesn't require the project maintainer to add language bindings or like support to in any form. And here in the presentation, you might find more details in the talk by Wim Lavrijsen, who is the author of that package. And so what is CPPYY in brief? So CPPYY is like, besides the naming, which is a little bit awkward, is like a C Python PyPy extension. So it is like an extension written to use the C API of either C Python or PyPy, depending on which one you use. And nowadays, PyPy has been kind of lacking a lot of development. So most of the new things are coming first in C Python. And it offers, as I mentioned, automatic on-demand mapping between C++ and Python concepts. So we literally map, for example, unique pointers to how this is done in C++, in Python, and so on. So we really think about semantics. And for better or worse, it's often neglected, but I think it's like an engineering marvel in language interoperability. And it relies on the on-demand reflection provided by the heavy root framework, which is challenging to, provide the swiftness of like evolution in terms of like what you would like do with a CPPYY as a binding tool. And the idea of our project was that it might be useful, or we thought it's going to be useful if we move CPPYY closer to the LLVM orbit and allow it to kind of evolve faster. The idea was that we want to be able to replace the CPPYY backend, which provided information from reflection information, with a specialized and more robust interoperability layer that has several properties which we thought are important for the longer term evolution and sustainability of that project. So one of them is easier adoptions of new LLVM versions. So meaning that we don't need to wait for 1 year or for 1 month or for to get a new LLVM version. That allows us to get Cuda standards or like C++ standards quickly, so that we can do proper mapping of the relevant C++ or Cuda or any other supported language entities. That would allow us to implement new features easily, because sometimes you need to change the reflection information layer, and that sometimes is problematic. It's going to have better, we thought, release cycle, and that would yield to wider adoption. So those were like the major points that we wanted to take. So we started redesigning the CPPYY backend with a project that's called CPPInterop. So this is like a library. CPPInterop is like a Clang-based library which provides reflection primitives that we wrote from scratch. That allows us to move a little bit different from the way that it was implemented when it was using the root framework. And in the major difference is that CPPYY would take and build like a huge strings and then pipe them through the incremental compiler and then take something back. But this was because the way that we provided the reflection information. Now with CPPInterop, we provide the reflection information as things go. So for example, we can provide much granular reflection information, which allows us to use inside the compiler the lookup tables, which have constant complexity of 1, which makes things quite more efficient. And in this syntax, see, so this here is Python. So we have a value where we say equals std.vector of int and then some initializer list. So this tells CPTY, because the way Python works is that Python wouldn't be able to find std, and it will issue a callback to a listener of ours and say, do you know std? And we'll say, yes, we know, because that's something from the C++ standard. It's going to build a special wrapper object, and then going next on the vector, it's going to ask the same question in the context of std. We're going to return that information, and so on and so on. And that proves quite a bit more efficient when it comes to, for example, template instantiations. And here you can see that in some maybe some of the pathological examples here, where we have like a deep nested template instantiations, or like a very long template parameter lists. Blue is our interop performance in terms of like memory, and orange-ish is the performance of the previous version of CPPIY, which was using the other reflection layer. So you can see that there's a good amount of improvement in terms of especially scalability. And this always, as I said, always done by using the most efficient code path inside the compiler, which is the name lookup in C++. Now, moving on, the goal of this CPPInterop library was to be able to, as I said, provide primitives for language interoperability, but they're not limited to Python. We tried to make them as generic as possible, because they, in the end, provide information about C++ and not to the other side of the language, which means that whenever we have like an API to instantiate a C++ template, it doesn't make, if the interface is good enough, it doesn't make a huge difference between whether we're going to do it within, whether we're going to call it within Python or D or Julia. But our focus was mostly to support Python. The way that we approached that problem, because it was like in the end, reflection in C++ is not the easiest thing to deal with. We created a document which describes the prior art, what has been done in CPPYY and CXXJL. So this is like a CPPYY-like package for Julia, which enables on-demand interoperability. And we enumerated the key features. We made a few revisions of that so that the experts are happy. And we implemented a proof of concept that's able to instantiate a C++ template on the fly within Python, just to demonstrate that concept in the beginning, so that people know where we are getting to. And we started connecting it to the CPPYY backend. And here, Bedenath Kundu was one of the people who spearheaded that work. And this is like a repository. It has like releases. It works with a bunch of, so it works with the Cling backend. It works with clang-repl 16, and it works with clang-repl 17. So it's pretty flexible. And here the key advantage is that I managed to switch the other day to support LLVM for like a couple of hours. Like we wanted to move from LLVM 16 to LLVM 17. It took me a couple of hours to change that and to be successful. And to support Cuda, it took me a day. So we have the clang-repl support of Cuda. I wanted to expose it so that we can run Cuda within the users of CPPInterop. It took me a day. So I think in the end, the flexibility is here. And that goal, at least to what concerns me, is quite well achieved. Now, the third pillar from our proposal was to enable access to heterogeneous hardware. Because data science is one of the things that, it needs to, especially for exascale, it needs to be able to adapt to the hardware that's behind it. So what we did is we designed and developed the interactive Cuda support. And here what I'm not mentioning, and probably I should, is that we built on what Simeon Ehrlich and the HZDR Institute has built in the past in Cling. But we improved a few aspects of it and we generalized it a little bit, which means that we found a way how to run incrementally Cuda code inside, say, a Jupyter notebook or inside like an incremental interactive environment. So one of the caveats is that the work here was especially challenging because these are proprietary codes and you don't get to see how they work. There's practically no documentation. They're like proprietary tool chains you can't disassemble and so on. So we figured out a way how we can ship PTX code in a different way from what Clang does through virtual file system overlays and so on, and that works quite well. So this is in release in LLVM 17, and here most of the work has been done by Anup. The other thing that was quite surprising to me is that our engine was able to find bugs in Clang mainstream itself from what concerns Cuda. For example, the way that they run the static initializers is quite different from what the Cuda compiler does, and we managed to detect that. We need to fix it somehow because that breaks quite a few kernels. And for example, we wanted to show today a ray tracer, but you get like an error 98, and then you need to scratch your head and figure out that 98 actually means that your kernel code comes after its uses. And that was part of the problem that we have discovered in Clang. We provided a fix and so on, but that's not yet all of it. There must be something else. Anyway, so that's there, and it's quite exciting because people were not even sure that that's possible in Clang mainline. What we did also is that we added OpenMP support, which was far easier than Cuda. Because the way that we have designed clang-repl is essentially we need to, and the way that OpenMP is designed and Clang is designed, we just need to include a header file and load the corresponding OpenMP library to get some parallelism out of the box. And that worked fairly straightforward. We're going to see that shortly in the demo. The other thing that we have done was to support new architectures in the JIT Link system. And as I said, the JIT Link system is a component that enables reuse of LLVM as an in-memory compiler by adding an in-memory link step in the end of the usual compiler pipeline. And if you're like a developer of say one of the major experiments at CERN, or if you are like a Numba developer that uses IBM platforms and so on, you have run quite a few times into inconsistencies in the auto implementation. But our project helped develop the more reliable JIT Link support for Windows. That's COF, and it's available in LLVM 16. So this is like a major thing. We are not even scratching it that much because it's not too important for data science, but this is like a major development. For 10 years, people that were wanting to use JIT and Julia and all of this on Windows, they had to switch to like a Unix format, which is called ELF, so that they can get some stability in their system at the cost of not being able to like make native calls or support things like comdat and so on. So Sunho here has made it that we support properly Windows, and that has like a major impact in performance and reliability. He also did develop the ARM for Unix 64 for Unix support, And that development actually provoked somebody else to hack in ARM32 support based on that work. So it was an external contribution. I don't know who were the people that were involved. clang-repl, I can claim that clang-repl also helped to establish the RISC-V JIT support. So there was like a Jonas Hanfeld here spearheaded that, and he was able to use clang-repl to JIT to interpret RISC-V code, which essentially was the first interpretation of that type of code, which is going to be a relevant architecture in the near future, from what I can see. And that's available, I think, in LLVM 16. The other thing is that our work there, and here thanks to Philippe Canal to establish some of the connections, is that we managed to also help developing or like finding a way to develop a PowerPC support, which is going to be available in LLVM 18, and that's contributed by LLVM, by IBM. In terms of tutorials and outreach, we wanted to have, since day one, very open environment and very inclusive environment. So we have an open virtual weekly team meetings. We have distributed team. We have had a distributed team over the years, and it's very challenging to find a good time slot because our team from time to time spawned from China to California, and basically there is only one possible time slot. But people who did the effort to essentially get up or like sacrifice some of their comfort. We also held and still holding virtual monthly meetings. We had over the past 3 years 13 invited talks by speakers from institutions such as Apple, AZDR, Quantstack, Max Planck, LBL, CERN, Electronic Arts. We also mentored students because education and student mentoring is one of the key aspects when we want to develop like the future engineers. And I'm quite surprised every time the amount of like talented people that we manage to find through these different programs. And over the years, we have had 2 unpaid contributors that just wanted to work with us. We had 2 CERN interns, we had 4 IRIS-HEP fellows, and we have 15 Google Summer of Code students. But here the count is a little bit, it's difficult to count because we use these programs complementary so that we can keep people for longer periods so that they can develop their skills and then contribute to our project, because this is compiler engineering and it's not an easy job. You can't learn it for like 3 months. So these programs we use complementary, and then some of the students we have used as an IRIS-HEP fellows, and then Google Summer of Code, and then CERN interns and so on. So there is some sort of like an overlap, but I think this played pretty well in terms of what we have delivered technically. We have had 3 technical documentation writers via the Google Season of Docs. We have done a bunch of presentations. You can follow up these links here and see more about them, because these are a subset of the presentations. And I think there will be at least 1 year of more things that we publish, because it was only the last year. The first 2 years we used to lay out the foundations of that basic infrastructure, and it was very difficult because we need to go through LLVM reviews and then establish ourselves in the LLVM community and so on. And the last year was the year that we managed to show, like from the user perspective, how these things are going to look like. And we have at least 1 year more to start publish the work that have been done and the nice use cases that we have enabled. So these are like the presentations that we have done, and they're a lot more, but I don't want to bore you with these details. We did some publications. We're planning a couple of more, and we have couple of more in the pipeline. The tutorials were something that we initially built quite a bit in the first in the first year probably, and then back in the third year we managed to get a tutorial in the PLDI. This is the top level conference for programming language design and infrastructure design and implementation, and there we had like 2 hours or 4 hours tutorial, I don't remember, where we taught people about how to build their programming languages using the LLVM components. And it essentially sums up all the JIT infrastructure, how we can set it up, how we can make a transformation of LLVM, and how we can use the incremental compiler as a service. And I think I probably, at the point of getting you bored, I wanted to go through a bunch of demos so that you can see what we have achieved over the last couple of years. So first thing, I wanted to go through our motivational demo, the way that we imagine things and how things turned out. So I'm gonna share my entire desktop. So do we have any questions up to that point? If not, I can just share my entire screen. Right. So here I have prepared a demo, which essentially I have Jupyter Notebook in a container on my local machine. Well, I have a local machine in the basement and then a local machine that gets to that basement. But the point here was to show that this is our mockup. I can just say, just having clear outputs. We define like a struct S, which is a C++ thing. And then we have like a special thing to say, instantiate a Python vector, which is an std vector of this S, which is connected here. Right? And put 5 elements in it. And then I can just run it. And then again, we use Python to print the content of the third or the fourth element of the vector. And you can see here, this is connected to this. Now, the next point is that we want to do something more fancy. We want to be able to derive from S. So this is like a C++ concept, and we want to derive from that concept and then use it, right? So here the whole point is that in certain cases you can have like a Python callbacks or Python interfaces which extend C++ entities, and then you can kind of combine together, enabling different use cases. Wim Lavrijsen has a bunch of them. If you have questions, how they work. And here you're going to see that we are like creating a class of that type, and then we're going to print it. So that's it. And here we have like a warning that tells us that, oh, well, okay, you use S, but you don't have like a virtual destructor. So Python is unhappy about it because it doesn't know how to destroy it, I guess. Now the next thing that I'm going to do is I'm going to have like a kernel in Cuda, which will combine, which will sum the elements into the sum variable, and gonna get like a x and a size, and then it's gonna do a sum over all the elements. And then there's like some Cuda boilerplate code that you need to go, allocate on the device, allocate on the host, and then here in that cell I have like some data where I'm gonna put some values inside. I'm gonna update the C++ part with the Python vector, and I'm gonna allocate what's necessary from the Cuda perspective, and then I'm gonna run the kernel. then I'm gonna print out the content. Now this is pretty close to what we thought, and here's like the resource, freeing the resource. This is pretty much where we want it to be. One last step that we need to take here in the advantage is to be able to kind of pipe it back to the res thing, like res val. So saying that we make a full loop going from C++ to Python to Cuda, and then going back to C++ through Python. And this is some code that we don't have here in that container for that demo, but it's a straightforward code, around 300 lines of code that we need to complete entirely the mockup, which to me is pretty amazing, because the way that at the time when we were kind of planning for this, we even hoped we have like a syntactic mistake here and so on, and we weren't able to even verify that until the very end. But anyway, we just imagine how that would look exciting, and now it's done. So that's pretty exciting to me. The other thing that we could do is I have planned to show you some OpenMP work. Here in this example, you can see, I can start. You can see how it works. So for OpenMP, we have like a specific kernel. So one of the weaknesses of Jupyter is that it's mostly designed, and the Zeus infrastructure is that it's mostly designed to deal with Python. And Python doesn't have too many options. You just run Python and then you get Python. But for C++, it has like all possible like flags and whatnot, which makes significant changes. So and to work around that, we have like multiple kernels like defined just for a simple flag. I think the Jupyter guys have like a proposal or RFC that is supposed to fix that problem, where you can just say, oh, and I want to run this kernel with these flags, which is going to be awesome. Anyway, so we take the OpenMP part, we take the hello world example, and then we run, and we get some threading capabilities. So here the advantage is that you can port very basic tutorials to use for teaching, but you also can use it for other purposes, because it's like a full-blown system behind. Then the next example, we're getting slightly more complicated examples. So we want to be able to mix Python and C++ and then demonstrate how that's going to fly with like a very heavily templated library, which is Eigen. So the idea of that example is to get Eigen, instantiate an Eigen matrix class with a Python type. And you can see here that we have, I'm not going to spend too much time on these tutorials because I have a bunch of more slides to show. What's important here is mostly the fact that we can combine these environments, and whether this makes sense from data science perspective in terms of like the particular demonstrations that we're doing is probably a matter of discussion, and we're happy to kind of improve it. So here, what we can do is we can install Eigen. I have installed it, but I mean, if I restart the container, I need to install it again. And then that would ask the package manager to like install what's supposed to install, and then get back to me, hopefully not in a long time. Yeah, it says it does something, and then it tells me it's installed. So here I can add the include path, through this. This is our CPPInterop, so it is the common denominator between the languages. And now I can have like a C++ cell which includes this eigendens and then creates like a matrix with a vector 2D, vector 3D, and so on. And here you can see we're using C++ 17. Then I can define like an operation, like eigen operations, which, does some computation, like a dot product and like norm and square vector norm and so on. And then I can go to, again, Python through CPTY and do the display part. And then go next. And then print all this from Python perspective. So this is Eigen, but the Python understanding of Eigen. You can continue on with like executing some Eigen operations via Python. I have matplotlib, but fine. Can install it then, and then we can plot something here, and then display again. Now, I want to go back a little bit, and I'm going to speed up the tutorials because I don't think I have too much time. I wanted to demonstrate showing a little bit of Cuda code here. So the Cuda code that we managed to run was vector addition. So we have, again, some Cuda header files here that we need to include. Here we have like a device printout, although we can do NVIDIA's me. Here we can programmatically take information about my basement super old Cuda card. And then I can do some vector addition here and then execute. So you can see my card here. And they can run it. So here the test is like we add two vectors, and then we have like a CPU vector that actually a CPU version so that it verifies that the results make sense. Going forward, I'm going to very quickly go through because this is one of the most complicated things so that you can see things can scale. This is going from C++, from Python to C++ to Cuda with interop to build a Kalman filter. So here, basically, the task is that somebody throws a rock from like a cliff, and then we make measurements. The point is to be able to demonstrate how we can compute fast the matrices and the vector operations via Cuda. We use C++ to get an efficient abstractions over these Cuda operations, and then for data processing and plotting, we can use Python. I'm not going to spend too much time on this. I will make the slides available. So can we start to clear the outputs? Still, we get that. We get like a basic textbook Kalman filter class. Then we can define the operations here that are required for computing the vectors and the matrices. Then the Cuda implementation, these are the abstractions over the C++ abstractions so that we don't need to write like over and over again this malloc and then take from the host, bring to the device and so on. Then the same thing for each operation. It's kind of heavy, but in terms of text. So where we are, at some point we're going to get to the interesting part, which is so let's do a sanity check. The matrix results look reasonable. So we instantiate the Kalman filter thing, and we initialize it. And then we do the measurements, set the data, we install the matplotlib, because not like we don't have it, but let's see. Then we take the measurements from this YAML Python library, then stuff it in back from like a vector back to the measurements that we have defined. And then we can use Python to plot the time, the position versus time. Of course, we can go on. And see how the process iterates. So we start with the data, and you can see here in the last element is how things converge. So we start from -14 and then go back to like 9 point something. We overshoot a little bit here and here, and then we need to get to the gravity kind of to the gravity. So here we convert to the gravity constant. I can continue here to show how this gets plotted. And here, this is one of the signs that our Kalman filter is kind of reasonable because it's exponentially converges. Can move on and show how the entire process has gone through. So we saw here we overshot a little bit, then we get to the optimal value. That's almost it. I'm getting to the end of this. So I wanted to demonstrate the Jupyter Lite infrastructure, so we are able to run C++ inside a WebAssembly. So if you go to WASM compiler research, you're going to get a demo. So this is like LLVM built in WebAssembly mode. And this is like an example code here, which will draw a bunch of rectangles. And this is going to be executed by our browser. So here you can see it. Now, we can probably use it at scale. So have like a small ray tracer here that I need to restart that again. Put it, the ray tracer. And I'm going to put, this is how accurate this thing is. So I'm going to put 12 so that I can see the image a little bit better. So this is like a C++ code that's written, that's using LLVM and clang-repl that runs in your own browser. So that doesn't have any dependencies, it doesn't go anywhere. So this runs inside your browser at native speed, because the WebAssembly actually goes that way. So we probably should do some comparison with like JavaScript or whatever, and then close to native. But you can see here that we can run, and we render the scene, and you kind of can see stuff. So that said, I think I'm going towards the end of the presentation. To sum it up, during these years, I think we have achieved some impact on science, which helped connect the domain experts with compiler engineers, simplify the data science infrastructures, at least in our major scientific domain, the field of energy physics, improve some of the Julia-based workflows via the JIT Link developments, improve the stability of the PowerPC area, which is also useful for NumPy. So that's going to be probably and NumPy on PowerPC platforms. And we also offer like a Jupyter-based educational environment to study parallel technologies such as OpenMP and Cuda, which is very important when you don't have like a good amount of infrastructure, or like you cannot afford cloud behind. And we also built an open and multicultural environment for advancing student skills and engineering in LLVM and the related software. In terms of like broader impacts, we have developed a good amount of technical and human capital, and in the intersection of compilers and data science. It connected domain scientists to LLVM community where core technologies. We managed to build some collaborations with industry. This project overall helped 27 young professionals from 11 different countries, some of who went to prestigious academic or industrial institutions, such as University of San Diego, ETH, CERN, University of Pittsburgh, IIT, Qualcomm, and Bloomberg. In terms of like future works, we should get out more demos. We are going to continue the open source meetings. We will continue bug fixing to stabilize clang-repl. We are going to merge probably Zeus CPP and Zeus clang-repl to show like a uniform interface for C++ for Jupyter. We need to publish our results on WebAssembly and online reoptimization. Here we didn't touch that at all. We will continue developing tutorials that illustrate use cases, and we want to reach out to new scientific domains to inform their communities for the new possibilities that we offer with our software stack. And here, a note of gratitude, because this is not a single person project. It is like a fruit of multi-year, multi-person effort that would have not been possible by you, who have been contributing or giving feedback or like contributing in any intellectual way. And our team, our compiler research team, would like to express our deepest gratitude to the various people who have contributed intellectual work in the area for that many years. And in conclusion, I think C++ can bring us bare metal performance. We can reorganize the existing tools and generalize them with minimal efforts to enable new opportunities. We should maintain and grow the tools that we have built, focusing on what they're good for. Many communities have multi-language expertise that can allow doing more science with the same budget if we can use the technologies for what they're appropriate for. And with that, I'd like to conclude. Thank you very much, and apologies for running a little bit late.